Hi there, welcome back. We're now going to talk about work and see how it's related to energy. We'll first define work and understand what it is, see how it's connected to energy, and then discuss the law of conservation of energy. Specifically, we'll see the conditions that are required for energy to be conserved, and then see what that means. Work is one of those terms that has a very different meaning in physics than it does in our common language, so we got to take some time to understand it. In physics, work is related to a force that moves over a distance. So in order for work to be done, I must have a force, and the force must move over a distance. Specifically, work is equal to the parallel component of the force times the displacement that it moves through. So for example, if I have the floor over here and there's a box sitting on it and I tie a rope to it and pull it as I drag it across the floor, I have a force that's the force of tension over here, and the force itself moves. So when the box is over here, the force is here. So the key thing here is that the force is moving, and therefore we have work. And since work is defined as the parallel component of the force times the displacement, here's my displacement. And so the parallel component of the force is going to be the horizontal component because that's displacement is horizontal. So here's my F parallel. And if this angle that the rope is pulled at is theta, then F parallel is simply F times cosine of theta because that's the adjacent side to the angle. And so in this case, the work is going to be F cosine theta times D, or FD cosine theta. If you remember our discussions of torque, that had to do with the perpendicular component of the force times the distance from it to the pivot point, and here it's a parallel component of the force times the displacement or the distance that the force itself moves through. Now, to emphasize the difference in this definition of work versus our common language usage, let's take a few examples. Let's say you're at the gym and you're holding some weights overhead like shown here. And let's say you hold the weight stationary for 5 minutes. If I ask you if you're doing work while you're holding the weight up, you'd say, of course you are. You are working hard to keep it there and keep it from falling onto the ground. But let's analyze the situation here. Are you applying a force on the weight? Sure you are. You're applying an upward force on the weight, which is what's keeping it from falling onto the ground. So there is a force being applied. The second condition is the force moving over a distance? Well, that's not satisfied. This force is stationary as you're stationary and holding the weight stationary as well. So regardless of how long you hold the weight overhead, the work you do is going to be zero. Now, if you wanted to convince me that you're doing work and you decide to take a walk across the floor of the gym while keeping the weight overhead at the same height, let's see what happens in that case. So now you still have a force that's pointing up, and you're moving the weight with the displacement horizontally, let's say in that direction. And so what's the parallel component of the force in this case? F parallel will be zero. Something that's vertical has no component that's horizontal. So even in this case, the work will be zero as you carry the weight across the gym, as long as you don't move it up or down. Okay, one more example to round this out. Let's say there is a wall here and you're standing on some skates and you push off the wall moving to the left. So now there is a displacement to the left, and there was a force when you pushed off the wall. But that force acted only for a very short period of time, so that was what we discussed before as impulse. That resulted in change of momentum for you, so you started moving. There is no continuing force that's moving with you. So there is no force in this case that's moving. So even in this case, the work would be zero. Okay, so that hopefully gives you an appreciation for how work in physics is different from how we use it in common language. Now let's understand a little bit more about work. I want to see what its units would be. So work would be FD cosine theta. F is measured in newtons. That's the unit of force in SI units. D, displacement or distance, is measured in meters. Cosine of theta has no units. So the unit of force is just Newton meter. which when we expand Newton, you'll get kilogram meter per second squared. And when I multiplied by the other Newton, you would get kilogram meter squared per second squared. And by the way, this is what we call joule. And so those are the units of work in SI units. You'll recall from just the previous video that these were the same as the unit of energy. And in fact, it turns out that work and energy are equivalent. Okay, one more point about work before we talk about its relationship to energy. Work is a scalar, just like energy is as well. But even though it's a scalar, it can be positive or negative. It's positive when F parallel, the parallel component of force, and the displacement are in the same direction. And it's negative when F parallel and displacement are in opposite directions. Now you might be wondering what a situation would be when the force and displacement are in opposite direction. There are several, and we'll take a couple examples coming up soon. Okay, let's move on to talk about the relationship between work and energy. And here's where it becomes very important to define what a system is. So if I have a system over here, it's got some energy. And the only way I can change the energy of the system is by doing work on it from outside. So when we said work and energy are equivalent, this is what we meant. Doing work can change the energy of a system as long as that work comes from the outside. And if it's positive work, the energy of the system increases. And if it's negative work, the energy of the system decreases. And so this is codified in this simple equation that says work from an external source equals change in energy of the system. Now this is change in the total energy of the system. And if you remember, this is analogous to the fact that impulse was equal to the change in momentum, which was the impulse momentum theorem. So let's take a situation when the external work is 0. So if I have work external equal to 0, what happens? Well, in that situation, delta E has to be 0, which means EI has to be equal to EF. And once again, this is very similar to the fact that if force external was 0, that is when we had momentum conserved. And by the way, this situation when external work is 0 and hence energy is conserved is what's called law of conservation of energy. And what we mean by EI equals EF is that the total energy of the system is conserved, which means that KI plus UI plus E therm plus other components equals KF plus UF plus E thermal final plus other components. So even though one type of energy can go up, let's say kinetic energy goes up and potential energy goes down by the same amount, in total the energy cannot change when it's conserved, which happens when the external work is 0. Let's say I toss a ball up, and when it's down here, it's got a velocity vi like that, and by the time it's gone up over here, you know that it's going to slow down. So let's say it's got vf like that. We're going to discuss this a couple of different ways so we can understand the importance of definition of a system and the relationship between work and energy. So first, I'm going to define my system as just the ball. In that case, we do have a force on the ball, so the force acts down, which is the force from the Earth, and because the system is the ball, Earth is external to it, and there is a displacement that the ball goes through. These two are in opposite directions. F parallel and D are opposite, and that implies that the work is negative. And it is an external work because the work is done by the Earth, which is external to the system. So when I have external work equals negative, my delta E is negative for the system, which means that the energy decreases. Does that happen in this case? Let's take a look. So this EF is less than EI. So this ball has kinetic energy. Does it have potential energy? Well, with the system defined as just the ball, there is no potential energy. Remember, potential energy is the interaction between two masses, and in this case I only have one mass. defined as the system, so the ball by itself does not possess any potential energy. And we're not considering thermal and other things here. We're going to ignore friction and drag and things that create heat. And when the ball is up here, I have a final kinetic energy. So when I say that EF is less than EI, I'm simply saying KF is less than KI because that's the only energy component that I have. And that makes sense. Remember, kinetic energy is energy due to motion, and it was just 1/2 mv squared. And the fact that it goes down is consistent with the fact that the ball slows down as it moves up. So we have seen how W external equals delta E works in this case. Okay, the other example I'm going to take is the system being the ball plus the earth, which is the more typical way we would handle this situation. So in this case, because the system is defined as both the objects, there is potential energy as well. So the energy will be kinetic plus potential. There is still a force between the two objects, there is still a displacement, but there is no external force in this case. Because the earth is now part of the system, earth applies a force on the ball in turn applies a force on the earth, internal forces cancel each other due to Newton's third law, and so there is no external force on the combined ball-earth system. Therefore, the external work is zero, and hence the change in energy would be zero as well. So we're now dealing with energy conservation situation. Okay, let's see how that plays out. So when energy is conserved, EI equals EF, and in this case EI is KI plus UI, and so that has to equal EF, which is KF plus UF. And I can rearrange this to say that UF minus UI equals KI minus KF. UF minus UI is delta U. KI minus KF is minus delta K, because change in something is final minus initial, so this is the negative of that. And so when energy is conserved and I only have kinetic and potential to worry about, I don't have thermal and chemical and other things, as one goes up, the other one has to go down. That's what this is saying. And let's apply that to our situation. As the ball goes up, what's happening to its potential energy? Well, here the height above ground is this much, HI, and here the height above ground is this one, HF. And since potential energy, you'll remember, is mgh, there is a ui now, and there is a uf, and uf is bigger than ui. The higher I am, the more potential energy I have, so the change in potential energy is positive. So this tells me that the change in kinetic energy must be negative, because negative of negative would be a positive, and that's consistent with the fact that the ball slows down. So when you toss a ball up, it's losing kinetic energy and transferring that loss to gain in potential energy, such that the total energy does not change because energy is conserved. So we can take the same physical situation and look at it two different ways, and it makes sense both ways. But it's very important to define what our system is and be careful as to what we consider the external force and external work to be in those cases. In this slice of physics, we understood work and saw its relationship with energy. First, we saw how work is related to a force moving over a distance, and work was given as the parallel component of the force times the distance it moves through. Then we realized that work is a scalar, but it can be positive or negative. And then we talked about external work done on a system is the only way to change the energy of the system, and the work done equals the change in energy of the system. Positive work increases the total energy of the system. Negative work reduces the total energy of the system. And finally, for an isolated system, which is defined as a system where there is no external work being done, the total energy is conserved. And we took some examples to talk through these things. Thanks.